we gave the definition that let f of z be analytic in a domain D. Then f of z is said to be univalent in D if for every 2 points z1, z2 that is in D, f of z1 is equals to f of z2 implies that z1 is equals to z2. So this is the definition of univalency that we gave.
Yes, sir.
In other words, two images are the same if and only if the points are the same. So now, and we have to look at examples. Now we want to look at under what condition can a function be univalent. That's what's called condition. So the first theorem we want to give is what we call Noshiro theorem. Noshiro theorem. It says let f of z be analytic in a domain D and on its boundary C. So f of z is analytic in a domain D and it is also analytic on its boundary C. If the real prime of f prime of z is greater than 0 in D, then f of z is univalent in D. So if this condition is satisfied in D, in other words, the real part, the derivative of the real part, every complex value has both real and imaginary part. If the real part is greater, and this real and imaginary part, they are real numbers. They are real numbers. If the derivative of the real part is greater than 0, then f of z will be equivalent. Then you take the part of it. If that is greater than 0, we are good to go. So let f of z be analytic in D and on its boundary C. There's a difference between the real part of the derivative and the derivative of the real part. The derivative of the real part means before find the real part, then you take the derivative.
Yes, sir.
No, but this one is not like this one. Before find the derivative
and look for the real part.
They are two different. Let f of z be analytic in a domain D and on its boundary C. Now let z1 and z2 be two different points. So we have our domain D and the boundary is C. So we take two different points, Z1, Z2. Now we know that f of z2 minus f of z1 is the same thing as the integral from z1 to z2, the derivative of f of z. We can always write, because if you find this integral, what will remain is what? F of z. You know that integral and derivative will cancel. F of z, then you evaluate it at the limit points, then you get this one. You understand?
Yes, sir.
So we can write f of z2 minus f of z1 like. On the other hand, let z be equals to z of t, which is equals to z1t plus z2 into 1 minus t. Here, 0 is less or equals to t less or equals to 1. So what we are doing now is that we are trying to find the curve between z1, this one, z that depends on t.
Okay.
So what we are trying to do now is that we have our domain D and we have 2 points, z1, z2. So we are trying to find this curve is what we denote by z of t. The line segment joining z1 and z2. Any line segment joining 2 points can be written in this form, where t is greater or equals to 0 and less or equals to 1. Is that okay?
Yes, sir.
Any 2 points can be written like that. Then we can find what is the z dt. Since z now depends on t, we can find what is the z dt. So if we find the z dt here, it will remain z1.
Yes, sir. Yes, sir. 7.
But if we find the z dt here, it will be minus z2. You understand?
Yes, sir.
Because z2 is a fixed point, so when you multiply z, it will go to 0 minus z multiplied by t. To find the z, it will be minus z. So this implies that our dz, we can write it as z1 minus z2 dt. We can transfer this dt to that side.
Okay, sir.
Is that okay? Let this one be equation 1. So, but this integral z1, z2 of df prime of z, that is the right answer. Now, we can write it as integral with respect to L, which is this one. L is the line joining 2 points, f prime of z of t into dz of t. dz. But this one will give us integral L f prime of z of t. But then we can just write f prime of z into dz will be z1 minus z2 the t. So which implies that this f of z1 minus f of z2, you know, this f of z2 minus f of z1, you know, is equal to this integral. But this integral now is finally by, because if you, this one is this one, you know, here you will find, when you want to find the derivative of this, it will be f prime, then derivative of what is inside, dz. So dz, but dz is equals to this one. That's what I substitute here. So which means that this integral that we started is the same thing as integral with respect to L, f prime of z Z1 minus Z2, the T. Is that okay?
Yes, sir.
We want to find the condition for the univalency. So if f of Z1 is equal to 10, this one will be 0.
Okay.
Is that okay?
Yes, sir.
And it will imply that integral with respect to L, f prime of Z into Z1 minus Z2, the T is equal to 0. You know that integral is 0 if only the integral, what is inside equals to 0. Now, if we have 0 here, then what is inside must be the reason why we have 0. But since real of f prime of Z, you know the condition is that the real of f prime of Z is greater than 0.
Okay.
This implies that f prime of Z is not equal to 0. You know, before a real value can be equal to 0, the real part and the imaginary part will be equal to 0. So if this one is not equal to 0 and we have 0 here, it implies that Z1 minus Z2 is equal to 0, which implies that Z1 is equal to Z2. That is, f of Z1 is equal to f of Z2 implies that Z1 is equal to Z2. And this implies that f of Z is univalent.